Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The chill of liquid helium, a realm approaching absolute zero, offered Walther Meissner a unique laboratory. This environment, a whisper away from the theoretical cessation of all atomic motion, became the crucible for his early investigations. He was drawn to the fundamental question: how do the familiar properties of matter, particularly its electrical and thermal behavior, transform under these extreme conditions? His early work, conducted in the 1950s and 1930s, laid the groundwork for a profound understanding of superconductivity, a phenomenon that would later bear his name. Meissner's initial focus centered on the electrical resistance of metals. At the time, the prevailing understanding, largely shaped by Heinrich Onz's pioneering work, suggested that electrical resistance would steadily decrease as the temperature approached absolute zero, perhaps even vanishing entirely. Onz, in the early 1910s, had already demonstrated the disappearance of electrical resistance in mercury below a critical temperature. His experiments, conducted at the Leyden laboratory, provided the experimental foundation upon which Meissner built. Meissner, however, sought a more comprehensive picture, investigating a wider range of metallic elements and alloys. He aimed to determine the precise relationship between temperature and electrical resistance, a relationship that, at the time, was still poorly understood. His experimental setup, though simple in principle, demanded meticulous precision. Meissner utilized a cryostat, a specialized apparatus designed to maintain extremely low temperatures. This cryostat, typically a double-walled container with a vacuum between the walls to minimize heat transfer, held liquid helium, the refrigerant that could reach temperatures approaching absolute zero. Within the cryostat, he carefully suspended the metallic samples he wished to study. These samples, usually in the form of wires or thin rods, were connected to electrical leads that allowed him to pass a current through them and measure the resulting voltage drop. The measurement of electrical resistance was a delicate undertaking. Meissner employed a sensitive potentiometer, a device capable of measuring extremely small voltage differences. By precisely controlling the current and measuring the voltage, he could calculate the resistance of the sample. He also meticulously controlled and measured the temperature of the sample using calibrated thermometers that were specifically designed for cryogenic use. These thermometers, often based on the temperature-dependent resistance of a platinum wire platinum resistance thermometer, were critical for accurately determining the temperature at which the measurements were taken. Meissner's experimental approach involved systematically lowering the temperature of the sample and meticulously recording the electrical resistance at each temperature step. He would then plot the data, creating graphs that depicted the resistance as a function of temperature. These graphs revealed intriguing and, at times, perplexing behavior. Some metals, as expected, showed a gradual decrease in resistance as the temperature dropped. Others, however, exhibited more complex behavior with sharp transitions or unexpected plateaus. These early observations, while not immediately revealing the full picture of superconductivity, provided crucial insights into the underlying physics of materials at extremely low temperatures. The challenges Meissner faced were significant. Maintaining stable temperatures, minimizing thermal fluctuations, and ensuring the purity of the metallic samples were all critical for obtaining reliable results. The purity of the samples was particularly important, as even minute traces of impurities could significantly affect their electrical properties. Meissner, therefore, paid close attention to the preparation of the samples, employing techniques such as careful purification and annealing to ensure that they were as free from impurities as possible. His work was not conducted in isolation. Meissner was well-versed in the existing literature and closely followed the developments in the field. He was particularly influenced by the work of Onz, whose pioneering experiments had established the foundation for cryogenic research. Onz, in his groundbreaking discovery of superconductivity in mercury, had demonstrated the potential for entirely new physical phenomena at extremely low temperatures. Meissner, building on this foundation, sought to expand the scope of these investigations, exploring the behavior of a broader range of materials and delving deeper into the underlying physics. The prevailing understanding of superconductivity at the time was still rudimentary. While Onz had observed the disappearance of resistance in certain metals, the underlying mechanism remained a mystery. The theoretical framework to explain the phenomenon was incomplete. The prevailing theories, based on classical physics, were inadequate to account for the observed behavior. The quantum mechanical nature of the phenomenon was only beginning to be recognized. Meissner's experimental work, therefore, was crucial for providing the empirical data that would eventually lead to a deeper understanding of superconductivity. This early research on the electrical and thermal properties of metals at liquid helium temperatures, while not immediately leading to a full understanding of superconductivity, provided the necessary foundation for his later, more groundbreaking discoveries. It was in this cryogenic environment that he would soon make a discovery that would forever change our understanding of the behavior of matter. Following the initial forays into the behavior of metals at extremely low temperatures, a pivotal moment arrived that would redefine the landscape of superconductivity: the discovery of the Meissner effect. This breakthrough, achieved in collaboration with Robert Ochsenfeld, unveiled the phenomenon that transcended the mere absence of electrical resistance, revealing a deeper, more fundamental property of the superconducting state. The scientific problem they addressed was the behavior of magnetic fields within superconductors, a question that at the time remained largely unanswered. The experimental setup was elegantly straightforward, yet incredibly insightful. Meissner and Ochsenfeld employed a cylindrical sample of a superconducting material, such as tin or lead, and placed it within a magnetic field. They meticulously observed the behavior of the magnetic field as the sample was cooled below its critical temperature, the point at which it transitioned into a superconducting state. Their primary tool was the measurement of magnetic flux penetration, using sensitive instruments to detect the presence or absence of magnetic fields within the interior of the sample. The observations were striking. Above the critical temperature, when the material behaved as a normal conductor, the magnetic field permeated the material. However, as the sample was cooled below its critical temperature and entered the superconducting state, something remarkable occurred. The magnetic field was expelled from the interior of the sample. The magnetic flux lines, instead of passing through the material, were pushed out effectively creating a perfect diamagnet. This expulsion of magnetic flux is the essence of the Meissner effect. To illustrate this with a specific example, consider the following. In one of their key experiments, Meissner and Ochsenfeld used a tin cylinder. They first applied a magnetic field and then cooled the cylinder below its critical temperature. Precise measurements showed that the magnetic field inside the tin cylinder was reduced to near zero. This was in stark contrast to the behavior of the cylinder above the critical temperature, where the magnetic field was present throughout the material. The data were clear and unambiguous, demonstrating that the superconducting state was characterized by the expulsion of magnetic flux. They meticulously documented these observations, providing quantitative evidence of the phenomenon. This expulsion was not a gradual process, it was a sharp transition, a definitive characteristic of the superconducting state. The significance of these findings cannot be overstated. It had been previously understood that superconductors exhibited zero electrical resistance. However, this observation of the Meissner effect revealed that superconductivity was more than just the absence of resistance, it was a distinct thermodynamic state. The expulsion of the magnetic field indicated that the superconducting state actively interacted with and responded to external magnetic fields. The material was actively excluding the magnetic field, a direct consequence of its superconducting properties. The implications for understanding superconductivity were profound. The Meissner effect demonstrated that a superconductor was a perfect diamagnet. A perfect diamagnet is a material that completely expels magnetic fields from its interior. This contrasts with a perfect conductor, which allows magnetic fields to pass through it without resistance. A perfect conductor, in the classical sense, would simply trap the magnetic field lines within itself. The Meissner effect, however, showed that superconductors actively push the magnetic field out. This distinction was crucial, as it highlighted that superconductivity was a quantum mechanical phenomenon, not a simple consequence of zero resistance. The enduring relevance of the Meissner effect lies in its fundamental role in defining and characterizing the superconducting state. It is a defining characteristic, a signature of superconductivity. The Meissner effect remains a cornerstone of our understanding of superconductivity. It is a key concept taught in physics courses, and it is essential for understanding the behavior of superconductors in various applications. From magnetic resonance imaging MRI to high-speed trains, the principles established by Meissner and Ochsenfeld are at play. The work of Heike Kamerlingh-Onnes, who first observed superconductivity, directly influenced Meissner's investigations. Onnes's discovery of zero resistance in mercury at extremely low temperatures opened the door to the study of superconductivity. Meissner built upon this foundation, exploring the properties of other materials and, crucially, investigating their behavior in the presence of magnetic fields. Onnes's initial observation provided the impetus, but it was Meissner who unveiled a deeper understanding of the phenomenon. The Meissner effect's impact extended far beyond the experimental realm. It provided essential evidence for the theoretical models that would follow. The most significant immediate influence of the Meissner effect was on the development of the London brothers' theory of superconductivity. Fritz and Heinz London, building on the experimental observations, formulated a theoretical framework that explained the expulsion of magnetic fields in superconductors. The Meissner effect provided the crucial empirical data that guided the development of their theory. The London brothers' work, in turn, laid the groundwork for more advanced theories, such as the Bardeen-Cooper-Schrieffer BCS theory, which provided a complete microscopic explanation of superconductivity. The discovery of the Meissner effect, therefore, was a pivotal moment not only in the history of superconductivity, but also in the development of theoretical physics. It provided a crucial piece of the puzzle, paving the way for deeper understanding of the quantum mechanical nature of matter. The Meissner effect, as we've seen, fundamentally altered our understanding of superconductivity. It revealed that the phenomenon was more than simply a consequence of perfect conductivity. A perfect conductor, as envisioned before Meissner and Ochsenfeld's discoveries, would allow a magnetic field to penetrate the material, albeit without resistance to electrical current. The magnetic field lines would remain within the conductor, flowing around any obstruction. The Meissner effect, however, demonstrated something far more profound. Superconductors actively expel magnetic fields. This expulsion, a definitive characteristic of the superconducting state, presented physicists with a new, complex problem. How could a material so perfectly conduct electricity also completely banish a magnetic field? This observation demanded a radical shift in perspective. Before the Meissner effect, the prevailing view was that superconductivity was primarily a consequence of the reduction of electrical resistance to zero. The Meissner effect, however, showed that superconductivity involved a more fundamental interaction between the material and the magnetic field. It suggested that the superconducting state was a distinct thermodynamic phase, a state of matter with unique electromagnetic properties. This was a critical conceptual leap, moving beyond a simple consideration of electrical current to a deeper examination of the material's response to magnetic fields. The Meissner effect, therefore, served as the empirical foundation for a new theoretical framework. The immediate consequence of Meissner and Ochsenfeld's experiment was the development of a theoretical framework to explain this perplexing phenomenon. This task fell to Fritz and Heinz London, brothers deeply immersed in theoretical physics. They were already familiar with the intricacies of electromagnetism and quantum mechanics. Their theoretical work, published in 1935, provided the first successful explanation of the Meissner effect. The London brothers, drawing upon the experimental data, constructed a set of equations that describe the electrodynamic behavior of superconductors. These equations, now known as the London equations, were a landmark achievement. The London equations are a pair of differential equations. They describe the relationship between the current density, the magnetic field, and the vector potential within a superconductor. The first London equation states that the curl of the supercurrent density is proportional to the negative of the magnetic field. In mathematical terms, this can be expressed as the curl of the supercurrent density equals negative a constant times the magnetic field. The constant is related to the density of superconducting electrons and the mass of the electron. The second London equation states that the time derivative of the supercurrent density is proportional to the electric field. This is expressed as the time derivative of the supercurrent density equals a constant times the electric field. These equations, though seemingly abstract, have profound implications. They predicted the expulsion of magnetic fields, the very essence of the Meissner effect. They demonstrated that the magnetic field could penetrate a superconductor, but only to a very shallow depth, a characteristic length now known as London penetration depth. This depth, typically on the order of tens or hundreds of nanometers, is a crucial parameter in understanding the behavior of superconductors. It represents the distance over which the magnetic field decays as it enters the material. The London equations provide a clear mathematical model for the expulsion of magnetic flux. Consider a superconductor placed in an external magnetic field. The magnetic field attempts to penetrate the material, but the superconducting electrons respond by creating a surface current. These currents flow in such a way as to generate a magnetic field that perfectly opposes the external field inside the material. This opposing field effectively cancels out the external field, resulting in the expulsion of the magnetic flux. The magnetic field is therefore pushed out of the bulk of the superconductor, existing only within a thin surface layer. This expulsion is a direct consequence of the London equations. The London equations, while a significant advance, are phenomenological theory. They successfully describe the behavior of superconductors. They do so without delving into the microscopic details of the superconducting state. They do not explain why superconductors behave this way. They simply provide a mathematical framework that accurately models the observed phenomena. This is a crucial distinction in the history of physics. The London equations were a first step, a necessary step, but they did not represent the final answer. They provided a framework that was later improved upon. The impact of the London equations on the development of superconductivity theory was immense. They provided a clear and consistent mathematical description of the Meissner effect, a crucial step in understanding the fundamental nature of superconductivity. They also laid the groundwork for more sophisticated theories. The London equations provided the foundation upon which later theoretical work was built. They introduced key concepts, such as the London penetration depth, that are still essential to our understanding of superconductors. Their influence is undeniable. The experimental observations of Meissner and Unveiler directly influenced the development of the London equations. The London brothers, armed with the experimental data, were able to formulate their equations. They were able to account for the observed expulsion of magnetic fields. Without the Meissner effect, the London equations would have lacked their essential empirical basis. The experimental observations were the bedrock upon which the theory was constructed. The legacy of the London equations extends far beyond their initial formulation. Their influence can be seen in the subsequent development of superconductivity theory, most notably in the Barton-Cooper-Schrieffer BCS theory. The BCS theory, developed in the late 1950s, provided a microscopic explanation of superconductivity. It explained why superconductors behave as they do. The BCS theory builds upon the foundations laid by the London equations. The BCS theory relies on the concepts introduced by the London brothers. The London equations provided the essential starting point for the BCS theory. The London equations helped to set the stage for the development of the complete microscopic theory of superconductivity. They remain a testament to the power of theoretical physics to explain complex phenomena. They are a lasting legacy, a cornerstone in the history of superconductivity. Following the meticulous experimental groundwork that established the empirical basis for superconductivity, Walther Meissner's investigations extended into the realm of high-frequency phenomena and the intricacies of material behavior. His focus shifted towards understanding how superconductors responded to electromagnetic fields oscillating at extremely high frequencies, a realm previously largely unexplored. This new frontier presented a unique set of challenges, demanding innovative experimental techniques and a deeper understanding of the underlying physics. Meissner's work in this area addressed the crucial problem of microwave interaction with superconductors. Before his experiments, the behavior of these materials under such conditions remained largely unknown. He devised sophisticated experimental setups, carefully controlling temperature, frequency, and magnetic field strength to probe the response of superconducting materials to microwaves. These experiments weren't merely qualitative observations. They involved precise measurements of microwave absorption and transmission through superconducting samples. He meticulously documented the power attenuation and phase shifts experienced by microwaves traversing these materials, providing quantitative data that was instrumental in shaping future theoretical models. A specific example of Meissner's detailed approach can be found in his studies of niobium, a material that exhibited particularly interesting superconducting properties. He painstakingly characterized the critical current density of niobium at various temperatures and microwave frequencies, revealing a complex interplay between these parameters. This meticulous characterization was far from an isolated study. It formed a cornerstone for understanding the limitations and possibilities of employing niobium in high-frequency applications. He further investigated the critical magnetic field of niobium under microwave irradiation, quantifying the field strength required to quench superconductivity under these specific conditions. This detailed experimental work provided vital information for engineers and physicists designing microwave devices. The impact of Meissner's work on the development of superconducting microwave devices is profound and enduring. His precise measurements of microwave absorption and transmission in superconductors directly informed the design of superconducting cavities used in particle accelerators and other high-energy physics experiments. These cavities, operating at microwave frequencies, require materials with extremely low energy losses to maintain high accelerating fields. Meissner's work on niobium and other superconductors provided crucial data for selecting and optimizing these materials for such applications, leading to significant improvements in the performance of these critical instruments. His findings were essential for advancing technologies that rely on the unique electromagnetic properties of superconductors at high frequencies. The influence of Meissner's high-frequency experiments extends to the broader field of material science. His rigorous approach to characterizing the properties of superconducting materials, particularly at high frequencies, established a benchmark for future research. Subsequent investigations into the behavior of superconductors under microwave irradiation built directly upon his foundational work. Scientists studying novel superconducting materials continue to employ similar experimental techniques, adapting and refining them based on the principles he established. His detailed characterization of parameters like critical current density and critical field remains a standard practice in the field, a direct testament to the lasting influence of his experimental methodology. Several physicists working on high-frequency phenomena directly influenced Meissner's research. The advancements in microwave technology during his time provided the tools for his investigations. The work of pioneers in microwave physics, whose advancements in the generation and measurement of high-frequency electromagnetic fields laid the groundwork for Meissner's experimental studies. Their innovations provided the necessary equipment and techniques for Meissner's detailed investigations into the behavior of superconductors at high frequencies. He built upon their achievements, extending their work into the specific domain of superconductivity. Conversely, Meissner's work directly influenced the generation of scientists working with superconducting microwave devices. His meticulous characterization of niobium and other superconductors provided essential data for the design of advanced microwave components. Physicists and engineers developing superconducting resonators and filters for communication systems and other applications drew directly from his findings. His work provided the empirical basis for the design and optimization of these devices, leading to significant improvements in their performance and efficiency. The high-frequency properties of superconductors, as elucidated by Meissner's experiments, became the foundation for a new generation of advanced microwave technologies. His legacy extends to the present day, shaping the development of cutting-edge superconducting devices. His contributions to the understanding of high-frequency phenomena in superconductors have had a lasting and far-reaching impact on both fundamental physics and technological innovation. The precision of his experimental approach and the meticulous nature of his data analysis continue to serve as a model for researchers in this field. The detailed understanding of superconducting materials behavior at high frequencies, largely due to his efforts, has opened up new possibilities in various technological domains. His work serves as a vivid example of how rigorous experimental investigation can lead to transformative advancements in both scientific understanding and technological applications. The exploration of Walther Meissner's scientific journey culminates in an assessment of his enduring legacy. His profound contributions, particularly the discovery of the Meissner effect, have indelibly shaped the landscape of physics and engineering. This effect, the expulsion of magnetic fields from a superconductor, proved to be a cornerstone in the understanding of superconductivity itself. It offered conclusive evidence that superconductivity wasn't merely a perfect conductor of electricity, but a fundamentally new state of matter. This realization fundamentally altered the trajectory of research in condensed matter physics, spurring decades of investigation into the nature of these exotic materials. The implications of Meissner's discovery extended far beyond the theoretical realm. The Meissner effect provided a direct indication of the quantum nature of superconductivity. The expulsion of the magnetic field, a phenomenon impossible within the framework of classical electromagnetism, demanded a quantum mechanical explanation. This, in turn, fueled the development of the Bardeen-Cooper-Schrieffer BCS theory, a landmark achievement that provided a microscopic understanding of superconductivity. This theory, formulated by John Bardeen, Leon Cooper, and John Robert Schrieffer, built upon the experimental foundations laid by Meissner and others. It explained how electrons pair up to move through a material without resistance, a phenomenon that could only be explained by quantum mechanics. The BCS theory, which earned its creators the Nobel Prize, stands as a testament to the power of combining experimental observation with theoretical insight. The work of Fritz London and Heinz London on the electrodynamics of superconductors prior to BCS had provided some theoretical framework, but it was Meissner's experimental validation that truly set the stage. Meissner's work also had a profound impact on the practical applications of superconductivity. The ability to levitate magnets above superconductors, a direct consequence of the Meissner effect, captivated the scientific community and the public alike. This demonstration of magnetic levitation, or maglev, became a symbol of the potential of superconducting technology. This phenomenon, where a magnet hovers above a superconductor, offered a glimpse of the future of transportation and other applications. This levitation, a direct result of the Meissner effect, has been harnessed in various innovative applications, including high-speed trains and advanced medical imaging devices. The study of high-frequency phenomena in superconductors, another area where Meissner made significant contributions, paved the way for advancements in microwave technology. His meticulous experiments and data analysis provided crucial insights into how superconductors behave at high frequencies. This understanding was indispensable for the development of superconducting devices that operate at microwave and millimeter wave frequencies. These devices have found applications in a variety of fields, including telecommunications, radio astronomy, and medical imaging. Meissner's impact extends beyond the specific discoveries and applications. His approach to scientific inquiry, characterized by precision, thoroughness, and a relentless pursuit of understanding, serves as a model for future generations of scientists and engineers. His meticulous experimental techniques and his careful analysis of data set a high standard for scientific rigor. This dedication to accuracy and detail has influenced countless researchers in the field of superconductivity and beyond. The legacy of Walther Meissner is not confined to the scientific community. His work has captured the public imagination, inspiring interest in science and technology. The demonstration of magnetic levitation, a direct consequence of the Meissner effect, is a particularly compelling example. The sight of a magnet floating effortlessly above a superconductor is a powerful illustration of the wonders of physics. This has fostered a greater appreciation for the potential of scientific innovation. The advancements in superconducting technology, directly stemming from Meissner's work, continue to drive innovation in various fields. Superconducting magnets are essential in medical imaging devices, such as MRI scanners, providing detailed images of the human body. They are also used in particle accelerators, enabling scientists to probe the fundamental building blocks of matter. The ongoing research into high-temperature superconductors holds the promise of even more revolutionary applications, including energy-efficient power transmission and advanced computing technologies. The enduring significance of Meissner's work is also evident in the ongoing exploration of quantum phenomena. Superconductors are ideal systems for studying quantum effects at a macroscopic level. The study of these materials has led to breakthroughs in our understanding of quantum mechanics. This understanding has opened up new avenues for the development of quantum computers and other advanced technologies. Meissner's legacy also encompasses his role as an educator and mentor. He fostered a collaborative research environment in which young scientists could flourish. His guidance and support helped shape the careers of many researchers who have themselves made significant contributions to the field. His willingness to share his knowledge and expertise has had a lasting impact on the scientific community. In conclusion, Walther Meissner's contributions to physics and engineering are truly remarkable. His discovery of the Meissner effect was a watershed moment, revolutionizing our understanding of superconductivity and its potential applications. His work on high-frequency phenomena in superconductors laid the foundation for numerous technological advancements. His meticulous experimental approach and his dedication to scientific rigor serve as a model for future generations of scientists. These discoveries and the impact they have had on the evolution of science and technology underscore the lasting significance of his scientific contributions. Meissner's legacy is a testament to the power of curiosity, perseverance, and the pursuit of knowledge. His work continues to inspire and inform, shaping the future of science and technology. His contributions remain a cornerstone in the history of physics, and his impact on subsequent scientific and technological progress is undeniable.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.